Hello, welcome everyone. Okay. So now, well, first of all, welcome everyone to afternoon session. First of all, let me comment that after Carlos' talk, the people that is doing the contributed talks of the next session have please meet there with David to explain them the technical details regarding their talks, okay? Okay, so now I think we can introduce Carlos Munera Jabaloy. In fact, he's from Alicante, but he studied the physics degree here in the University of Valencia. Then he went to Bilbao, to the University of Basque Country, to study the master's degree in quantum science and technology. And he stayed there for pursuing his PhD in nitrogen vacancies in diamonds. And then now he's a postdoc in Ulm, in the group of Martin Plenio and Susana Huelga. So please, Carlos, whenever you want, the floor is yours.
Thanks. Okay, can you hear me? Yeah. So first of all, I would like to thank the organizers for inviting me. And my talk is going to be an introduction to NV centers and quantum control, and I hope you can take something home. So I will start by trying to to present these two machines. You've probably seen at least one of them. This is here an NMR spectrometer. They are very common in chemistry labs and universities. And that thing there is an MRI machine, which you can find in hospitals. Now, this is very old technology. This is 50 years old, 60 years old, very old. And the way this thing works is inside these two machines, there is a very powerful magnet. We will put a sample inside. The sample could be a chemical substance or could be a person that you want to see inside. And then this extremely strong magnetic field is going to align the spins of this person. Then there are some coils which are going to introduce some radio frequencies that will interact with these spins, and then the spins will generate a magnetic response that we can measure, and we can obtain very valuable information. So the chemical substance that was in the sample that we put inside, or the tissues inside a person. So it's old and very useful technology. Now there is something which I would consider an evolution of these old technologies, which is color centers. So color centers are spins that are trapped inside of crystals. In this case, this is an experiment on MV centers, which is the thing I will talk about. These are spins that live inside of diamond. And this is how it currently looks. So it's all experimental. These are optical tables. And then this is what you would see. So a lot of lasers, a lot of mirrors, and antennas. But the idea behind is very similar. You will also find a magnet. You will also find spins. And you will also find antennas. Now, how do these two technologies relate to each other? First of all, in a bit more detail, this is an NMR machine. So we have a sample with a lot of spins. And a lot of spins means a macroscopic number of spins, so millions and millions and millions. We have our coil. It's just a classical coil, so there's nothing quantum there, only in the sample. And then we apply a radio frequency. And here we are doing something which is matching the magnetic resonance condition, which I would argue is one of the oldest coherent quantum control techniques there, but it's still quantum. And then these millions of spins are going to respond, and they will generate a very weak but classical magnetic field that we can detect with the coil, and then it will induce an electric signal, and we can get some information. And this information is very valuable. It's valuable enough for us to build these multi-million machines that are present everywhere. Now, the way these color centers work is now we have a single spin. So this is the big difference. Now we don't need a classical sample. We can work with only one of them. We will still apply the magnetic resonance condition. We will manipulate the spin. But now, of course, we cannot trust a weak magnetic field to measure this spin. It's just only one. So thankfully, these spins allow us to measure them through fluorescence. This is, we will apply a green laser, in the case of DMB. We will measure some fluorescence, and from this fluorescence that we are measuring, we get, again, a signal with valuable information. So let's see more in detail. Now, this is indeed the nitrogen vacancy center. So it is a diamond pond defect. So this means it's a little error inside the diamond lattice. That thing there is the diamond lattice. There's a bunch of carbon atoms in a structure that repeats. And then the nitrogen vacancy center forms in the following way. We lose one of the carbons. A nitrogen appears there. And then we lose another carbon contiguous to it. And that's what we call the vacancy. Now, a bunch of electrons will get inside this vacancy. And we can find these nitrogen vacancy centers in three charged states, which are positive, neutral, and negatively charged. The negatively charged is the one that's most commonly studied and the one I will talk about. And as I mentioned, these defects interact with light in a way that's very useful for us. The way they interact is that they emit red light. And in fact, if you find a diamond that's full of nitrogen vacancy centers, it will be pink or maybe even purple. So it's very nice. And this is with more detail how this works or why it works. This is the energy level structure, a simplified diagram. And so we have electronic spin 1 triplet in the ground state, electronic spin 1 triplet in the excited state, and then we have a metastable right there. The way it works is that when we shine a green laser, we are going to excite our electrons, and then they may fall emitting red light. However, the 1 and -1 could with a high chance, go through the metastable, and this translates into the 1 and -1 emitting less light. So this is the 0 state is brighter. Here we can see a graph from an experiment. This is from the group of Christian Degen, and this shows really, with respect to time, if we are in the MS0, so this is the intensity of the light we will receive, it will be higher than the -+1 states. And this allows us to measure the state of the MV very easily. Not only that, but also the steady state is going to be the 0. So if we keep this process, if we keep shining light, we will end up polarizing in the 0 state. So now we can initialize the MV, we can measure it, and this is really two conditions that we need in order to have a useful qubit. And one of the most important characteristics of this MV is that all of this can happen at room temperature. This is very peculiar, and it's the reason that they are so useful and so widely spread as quantum sensors. So now we can forget about all of that and just focus on the triplet ground state. Really, we just have to think that the 0 is brighter than the other two, so we can measure it. And then the way it works is this is the Hamiltonian. So we have spin 1 matrices there, a set. Then we have a 0 field splitting. This is just a constant that appears there that's splitting by default the 0 and the other two levels. And then if we apply an external magnetic field, we will have some Larmor splitting that will split the +1 and -1. OK. Now, let's see how we can control this type of defects, and in fact, how we can control any system in NMR. So let's think about a simpler system now. It's just a spin 1/2. So it could be an atom of hydrogen inside your body, for example, for MRI. This is the only Hamiltonian we really need to understand, which is the Zeeman interaction. So this is the thing that is behind everything. It's just the interaction of a spin that has a magnetic moment with an external magnetic field, which can be arbitrary. The way these experiments are usually set up is something like this. So we have a strong magnetic field along Z, which is our quantization axis. And then we are going to introduce a driving in the orthogonal plane, which is going to change as a cosine with a frequency omega d. And this is going to be a perturbation. And this is the scheme I have in mind. So we have our splitting due to this first quantization axis, this first term, and then our driving. And through the magnetic resonance condition, we are going to be able to transfer population from the 0 to the 1. Now let's see this in more detail. This is exactly the same Hamiltonian. I just rewrote it a little bit so it's less ugly. We have the splitting omega 0, and then the strength of the driving is just big omega there. Again, this is the free energy, the quantization axis. This is the perturbation. And when we have this type of situation, where our perturbation is time-dependent, a very useful technique that we use all the time is the interaction picture transformation. So the way it works is we will obtain an effective Hamiltonian, which is physically equivalent to the other one. So this Hamiltonian represents the same physics as the other one, but it's a useful transformation to make. And for us, it will allow us to get rid of the time dependency, which is not nice to work with. So to do so, we just apply the propagator of H0 to the perturbation. This is the same thing expanded, okay? Just a little bit ugly, but it's exactly the same thing. And now the nice thing is that these propagators are diagonal. So we know exactly how they act on the 0 and the 1. And what they will do is put some rotating terms inside our sigma x. This is now our Hamiltonian in this interaction picture. Next step is going to be expand the cosine. So we end up with these 4 rotating terms. Now we can put everything together, okay? And here is the key step. Now we have a term that's rotating as omega 0 plus omega d, and a term that's rotating as omega 0 minus omega d. Then here comes the magnetic resonance condition, which is to say our driving is going to match the splitting. So we choose omega d to be omega 0. With this condition, we end up with this thing. So now we have one term which is not rotating, and a term that rotates very fast inside of a small perturbation, if you remember. Then there is a very useful approximation we can make, which is we have a weak term, the perturbation, that's rotating very fast. So we can just neglect this part here. through the rotating wave approximation. And we end up with this very simple Hamiltonian, which tells us, OK, if you match the resonance condition, so your driving has the frequency of this splitting, you are indeed going to create a population transfer at a rate which is given by big omega. So we end up with that Hamiltonian there. OK. Now, let's see an easy experiment we can do with this thing. We will take a spin 1/2 system, so two-level system. We will initialize it in the 0 state, and then we are going to measure it after applying some driving for a short amount of time. So this is the thing we expect to see. The moment we match the resonance condition, we will see some population transfer, and then we will lose some population in the 0. If we don't match it, we will not see such a thing. So here, x-axis is the frequency of the driving, y-axis is the probability of finding 0, and then let's check 3 spots. So for example, here we are applying a driving, but the frequency is too low. So we are not transferring population, and the population stays in 0. Here we exactly match this condition. We have population transfer, we see a dip. This is the magnetic resonance. And finally, we could also apply a driving with a frequency which is too high, so nothing happens again. Now, is this thing real? Of course it is. It is real and very old. This is 1938. This is the first ever magnetic resonance. It was done by these people here. And the way they did it is with a beam of molecules through a Stern-Gerlach experiment. So this beam would get deflected depending on the spin state. And then before this Stern-Gerlach, they would apply a radio frequency with a magnetic field. The moment they matched this resonance condition, the beam would deflect to the other side, and then we would see this peak. And this same paper, which is extremely short, it's just 1 page, gave Isidor Rabi a Nobel Prize for the discovery of magnetic resonance. OK, but this is all two-level systems. What happens now with the MV? As I said, we have 3 levels. And you could repeat exactly the same derivation we did, now with the spin 1 matrices. We are not going to do that, but I can tell you the result is that now there are 2 resonances. One is between the 0 and 1 state, so the 0 and the higher level, and the other resonance is between these 2 other levels. So now we expect 2 peaks. And the interesting thing is that before it was a classical beam of molecules, so really many of them. Now we could do it with only 1, because the 0 is brighter than the others. So this is the first ever optically detected magnetic resonance. So a magnetic resonance that's detected through the fluorescence of the crystal. This is the first ever by Gruber, Bragtrup, and so on. And here you can see the 2 peaks. The top example is with an ensemble. This means there are many MVs. They just check, and indeed they see this fluorescence profile. Again, y-axis is the fluorescence of the crystal, and then the 2 others are with only 1 defect. Again, there are 2 peaks, but they are very close together. So, can we use this for something? Well, luckily, yes. As I told you, if you remember, this is the energy levels that we have through the Hamiltonian, so the 0 field splitting, but then we have this extra splitting due to the Zeeman effect. So this is, if there is an external field, an external magnetic field that we may want to measure, then these 2 levels are going to split apart. This means these peaks will separate with a frequency separation which directly depends on the external magnetic field applied. We can use this experiment in order to measure magnetic fields. This is an example, again, from the group of Degen. Single MV in both of them. They are measuring the luminescence. They sweep a microwave drive. And then here you can see 0 field, so no magnetic field. Both levels are together. We only see 1 peak. And then in that case, 4.4 millitesla, the 2 peaks split apart. And the other way around. If you measure this spectrum, you see these 2 peaks, you say, OK, there was 4.4 millitesla. And this allows us already to do some technology. And here are some examples. Well, first, a small recap. The MV center can be coherently controlled at room temperature, which is very peculiar. We can very easily measure these splittings through microwaves and fluorescence. So it's a really easy setup, relatively easy. And these energies are sensitive to physical quantities. I told you about magnetic fields, but really they also are sensitive to strain, to temperature, to electric fields, so we can measure many things with them. And then 2 examples I like a lot. These are some tips that are fabricated by a company called Konami, and this is all diamond. So they build these structures in diamond, and they have this pillar there, a small tip. And just in the tip of the pillar, there is a single MV. So the thing that they do is they have a machine, and then they can scan a sample. There is a laser shining here, and then they can perform ODMR in a lot of very small regions of this sample. This is, in the end, they obtain a very high-resolution map of the magnetic fields of the sample. And this, in fact, is allowing already to do some discoveries outside of quantum technologies. For example, in paleontology and geology, these tools, for some reason, are very useful. And here is an example of one of these maps. This is from the group of Degen, again. They are also developing this type of technology. And this image I like a lot. This is a superconducting material. They are scanning it. And the 2 black dots that you can see there are superconducting vortices. So they can image vortices by scanning this tip. Now, a different example, this time from the group of Michał Lukin. This is, again, using ODMR. But now we are not interested in the splitting. What we are interested in is in the central frequency. Because the central frequency, the zero-field splitting, is going to tell us about strain, but also about temperature. And this is the thing they are interested in. And the experiment they did was take nanodiamonds containing an MV. So this is a very small diamond with 1 MV inside, and then they gave these nanodiamonds to cells. And here, for example, is one cell that ate 2 of these nanodiamonds. Not only that, they also have a heat source, which is marked with a cross. It is a gold nanoparticle that they can heat up using a laser, and then they can track how the temperature of the cell changes in 2 different positions. So it's a way to create very small and precise thermometers. So cool experiment. And then, if there are any questions, if not, we can stop 10 minutes. Yeah? Yeah.
Yes, that's like an AFM tip, or it doesn't have anything to do with that?
So it's a very similar idea. Again, it's a very small tip that they can scan on a sample. So in that sense, it's the same idea. But instead of measuring forces or measuring tunneling, they have an NV on the tip, and they are measuring the ODMR in many positions. So this allows them to measure the static field that the sample is generating in many different places. So for example, there, in this case, they can see the vortices in a superconducting material.
OK. And they have the same spatial resolution?
So I don't know no, I mean, this is much smaller than an AFM, so they cannot see individual atoms with this technology. But if I am not wrong, this is the technology that allows the biggest spatial resolution to measure magnetic fields. But it's not in the level of AFM currently.
Thank you.
OK.
Any more questions?
OK, so we wait 10 minutes. 10 minutes. OK.
And we come back.
No, no, no.
Y luego cuando la cuestión...
Sí, ¿eh? Okay. Is this connected? Yeah, okay. So let's see now the second part. This time is going to be pulse control. So we learned the very basics on how to control the MV in the most basic way possible. Now let's go a step beyond and learn a little bit about pulses, which is really the thing that people do in the field. So first of all, what do I mean by a pulse? A pulse is just the thing we learned before, so a driving, but now it's going to be short and usually powerful. And we apply many of these pulses in order to control these systems. To understand them, the first thing we do is spin 1/2 is, spin 1 is too complicated for us. We are not going to work with 3 levels. We will forget about one of them. And then we will just pretend that it's a qubit spin 1/2. Of course, one can do things with the 3 levels, but it's a very common trick to do. And as we are now thinking that we have just a qubit, we can use the same mathematics as before. So this is the same Hamiltonian I used, but now I allow an extra degree of freedom, which is my driving cosine of omega dt now can have an arbitrary initial phase, so this phi. If we repeat all the calculations, we will end up with this effective Hamiltonian. It's exactly the same thing as before, but now the thing that was a sigma x before, now we can choose. It could be a sigma x, it could be a sigma y, sorry, or it could be something in between. This is phi will be an axis in the equator of the Bloch sphere. So now, how does the propagator of this thing look like? Looks like this. I will define 2 parameters, phi and theta, which is really all I need to describe a pulse in this level. And then this is my Hamiltonian minus I big omega over 2 sigma phi t. And this omega and t, of course, is just the amount of population I am going to transfer. I can put them together into just 1 parameter theta. And this, for people who is doing quantum computing and so, I checked in Wikipedia, and this is the definition of rotation operator gates. I was curious, and indeed, if you see these exponential forms, it's exactly the thing I just wrote. So every time you hear people like me saying pulses, 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 what we mean is single qubit gates. Okay, it's exactly the same. In particular, it's exactly these ones, rotation operator gates. This means that using pulses, we can apply arbitrary single qubit gates onto our MV center. And why do we use this language? Why do we say a pi pulse over x, a pi half pulse over y? Because it's a very useful language because it can be visualized very easily. So for example, let's take this thing here. It's going to be a pi pulse on x. If we go to the Bloch sphere, what this does is a rotation of 180 degrees around x. So it's very simple to map this language, the language of pulses, into transformation of the Bloch sphere. On the other hand, if we talk about a pi half on y, it's going to be a pi half rotation around y. So nothing unexpected. And in fact, these 2 types of pulses, pi and pi half, is the thing we are going to use the most. So we will use pi half pulses in order to prepare superpositions from the 0, and in order to map these superpositions into populations. And we will use pi pulses to do refocusing, which I will explain in a couple of slides. we need just one last idea, which is, OK, if I have a signal, a magnetic field, for example, how do I measure it? So let's go to our original Hamiltonian. Now I am not driving, and I have just this omega 0 over 2 sigma z. So this is just the splitting. If I have a small magnetic field that I would like to measure, what is going to happen is that I will have a small shift, which is going to be this delta over 2 sigma z. Now, I already did some interaction picture transformations, and of course, we need to always work in the same rotating frame. So I will do the same transformation, and this is the effective Hamiltonian in the end, just this delta over 2 sigma z, which of course, in the Bloch sphere, is just a rotation around z. This means if we find a way to measure the rotations we do around z, it is a way to measure signals that we could be interested in. This is shifts that are happening to our qubit. And there is a very easy protocol we can already understand. It's called the Ramsey sequence, and it works in the following way. We start by initializing our qubit, so we apply a pi half, so we go from 0 to a superposition of 0 and 1. Then we let it evolve freely, we don't do anything, and then this signal that we want to measure is going to introduce a relative phase in our superposition. And finally, we do a pi half, we map into population, and we measure using a green laser, as you already know. And there are two examples here. So we initialize, now we have some shift, and then we map into population. And here is another example with a little bit more phase, so you can see indeed that the height is different. This is, we will be able to detect this difference through the fluorescence. OK, but we already knew how to measure magnetic fields. We already knew about the ODMR. What is the advantage of this? First of all, it's more sensitive, but also allows us to create more sophisticated things, for example, in order to measure oscillating fields. Okay? So what is the problem of measuring oscillating fields? Let's imagine this is a signal that's acting on our MB. The pi half pulses are just one period apart. So let's see what happens. We prepare our superposition. We are going to accumulate a little bit of phase in one direction, and then we will lose the phase that we just accumulated, and then we did nothing, right? We will map into population, and we will see absolutely nothing. This is, the Ramsey sequence is not suited to measure AC signals, and that's sad, because we would like really to measure radio frequencies or different AC signals. But we only used pi halves. Let's now use the pi pulses. So this is the so-called refocusing. Let me expand this evolution in the propagator. So I just wrote the propagator of one of the pulses, the propagator of the free evolution. This is minus delta, the propagator of the other pulse. Now we can use a trick. Of course, this pulse and that other pulse are the adjoint of each other. So if we multiply them together, it's the identity. We can use that property through this mathematical relation. It's very easy to show, but we can make them act on the Hamiltonian. And I will not talk a lot about the details. This is, again, very easy to show. The end result is that it is the same evolution as in the beginning, but now the delta changed the sign. So if we take some free evolution, we put it like a sandwich with pi pulses, we change the sign of this phase. Let's see this graphically. Here is a normal evolution. We accumulate a little bit of phase. Now with pi pulses doing a sandwich, this time is y, doesn't matter really. So first we do a pi pulse. Now we accumulate the phase. And now we do another pi pulse. And if you see the end result, it's exactly the same thing, but now it's in the other direction. So this is the trick that we need really. And we can take now our Ramsey sequence, we modify it by making this sandwich, and now it has a different name, the spin echo. If you remember from the previous slide, this thing, we know what it does. It just flips the sign of this phase. And so it would be a Ramsey in which both parts of the wave are positive. And this thing indeed measures AC signals. Not only that, but it's also sensitive to frequency. This is all this thing I show you taking into account that one oscillation perfectly matches here. If that is not the case, if this frequency is higher or if this frequency is lower, we are not going to accumulate any phase. So this sequence here allows us to measure a signal of a particular frequency. And then we can extend it. Of course, we don't need to measure only one oscillation. We can measure more of them. This is now called the CPMG sequence. And in fact, we can simplify it. It's very easy to show, but the idea is the same, that we don't need to do -x, and we can spare the last pulses. And this is the form that everybody uses. Works exactly the same. And with this thing now, we can measure oscillating signals, finally. So, small recap. Pulses allow us to execute single qubit rotations. With this, we can measure oscillating weak signals. The MV is very sensitive, so it would be very nice to use it. And what can we do that's useful by measuring oscillating magnetic fields? Of course, we can do NMR, which, as we saw, it's a very, very nice application that people would like to have. So finally, let's see NV-based NMR. There are questions about this part. OK. Yes? I can send you this. OK.
How do you know how much time do you have to put between the pi pulses?
Yeah, that's a very good question. Should have said that. So the way that this type of experiments work is you don't know. You take your sequence, you do it, and now you repeat, but you change slightly the time. And then you sweep the time between the pulses, and then you are looking to the full spectrum. That's the way you are going to detect.
OK, thank you.
OK. So now let's see how we can do NMR using MVs. So the idea is going to be same thing as before. We have our sample. We do something using an RF radio frequency. Now we know what it does. It is a pi half. So we take our spins, we rotate them, they start to precess, and we want to know the frequency of this precession with a lot of precision. This will emit an oscillating signal. It will be picked up by the coil, and then we will do NMR. But now we take the coil, and we put an MV. Okay, this is the full idea. This is how the setup would look. So we have a slab of diamond here. We have MVs inside this diamond, and the sample on top. In this case, for example, is ethanol, could be whatever. And then we have an external magnetic field. We will do something on this sample to make it emit a signal, and then something on the MVs to receive this signal and measure. Now, why would we want to do this thing? Why not just use our normal classical NMR machines? The very nice promise of this technology is that now we should be able to measure extremely small volumes. So this could be extremely, extremely small, and that's something that classical NMR machines cannot do. And a bit the dream of this field is people would like to put a single cell here and then do NMR of a single cell, which is, of course, totally out of the question for classical NMR machines. And this is a bit the reason for people to pursue this technology. OK, and this has been done. This is an example, for example, 2015 by the group of Ronald Walsworth. This is the sequence they used, very similar to the thing we've been looking at. They just changed a little bit the phases of the pi pulses because it's a little bit better, but it's exactly the same idea. And that's the spectrum of some substance that contain fluor and hydrogen. And indeed, you can see two peaks here. So NMR solved or not, because now let's see how good is this. This is the quantum NMR, and that's a classical NMR, again, of ethanol. So for example, all of these peaks come from hydrogen. Why do we have so many frequencies coming from hydrogen? Because they are in different positions inside of a molecule. So just by being in different positions in a molecule, their precession frequency is slightly different, and we can see all of these peaks. And this is what a chemist needs in order to say, OK, it was ethanol. However, here, if you look at the hydrogen, it is only one blob. Okay? So something is not working. We are not seeing the same thing. This is, although this is a extremely big experimental achievement, it's nowhere near the classical counterpart. So classical wins, sadly. Now let's see why. The reason is the following. If I show you this signal and I ask you what is the frequency of this signal, it's not so easy to say, right? You can maybe count, OK, 1, 2, 3 oscillations, I don't know. So it's not so easy for you to tell me the frequency of this thing. And in fact, we can quantify this by taking a Fourier transformation. And so the spectrum looks like that. It's a peak, but it's a very broad peak. What happens instead if I give you more time? Now you can count a lot more oscillations. You have a lot more certainty when giving me an answer. And also, the Fourier transformation shows me a narrow peak. This can be stated with the following formula. The resolution in frequency that we have goes as 1 over the time we measure. This is, we want to measure for a very long time to have very high resolution. And that's what we need to do NMR that's really useful. OK, so now let's calculate what happens with the MV. Let's say that the MV lifetime is like 10 microseconds, more or less. So this means we will have a resolution of 100 kilohertz. OK, classical NMR can do hertz, 1 hertz, maybe less. So this means classical NMR is 100,000 times better than MVs in this case. OK, but thankfully, people thought about a trick. And the trick is the following. Let's revisit our CPMG. I told you it's sensitive to frequency. This is, if the frequency is not matching exactly, it's not going to work. But it's also sensitive to something else. It's also sensitive to phase. This is exactly the same frequency, but now it's a cosine instead of a sine. And now if you check, this part here is going to cancel this one. This part here is going to cancel that one, and so on, and so on. This is, even though it's the same frequency, I just changed the phase, and now I don't see anything. While if it was a sine, I do see something. This is the CPMG. It's not only sensitive to frequency, it's also very sensitive to phase. And this is a trick. So how do we use it? Let's imagine we have a signal, which is the thing on top, OK? Just a very coherent signal that we want to measure. Maybe it comes from our sample. And now what we are going to do is a lot of CPMGs, and then I put them all with a difference of tau time. So I do one sequence, I wait tau. I do a sequence, I wait tau, and so on, and so on. Of course, each of these sequences is just 10 microseconds, 20 microseconds, so the MV is within its lifetime, but the full thing is much longer. And then let's see what each of these CPMGs sees. If I block everything else, they all see exactly the same. Okay, I created this example to say, OK, maybe this is the case. Tau is just an integer number of oscillations, so they all see exactly the same thing. This is, all of them are going to give me exactly the same value. If I measure, all of them will give me the same. Now I am going to change this frequency very slightly. OK, this is just to mark the initial phase. And now, visually, it looks the same. I change this frequency a little bit, and now if I do the same, as you can see, the initial phase is completely different. Okay? This is the trick. If now I measure, I will obtain different values in each measurement. And the relationship between these different values gives me information about the frequency of this other signal. And if I now ask you, for how long did I measure? It's not true that I only measure for this, because the measurement is everything. So this is a way to decouple the MV from its lifetime. We can measure for much longer. Okay? This could be a phrase. Continuous sampling sequences, which is this thing, allow us to measure for much longer than the MV coherence time. So this was published at the same time by two groups, one in the University of Ulm by the group of Fedor Jelesko and Martin Plenio, the place I work right now, and then also by Degen, of course. And this is from one of the papers. As you see, it's exactly the thing we were talking about. They measure many times, and they detect the phase in different points in time. And that's enough to do a high-resolution spectrum, which was done for the first time in 2018. This is by the group of Ronald Balsworth. And now, this is much closer to the classical thing. This is only hydrogen. We see different peaks for different substances. So yeah, first ever high-resolution NMR. So now a small summary. DMV is a very nice sensor to do quantum sensing because it works at room temperature. It's very easy to work with. We can use microwaves to control them. They can sense static magnetic fields, oscillating magnetic fields, temperature, a lot of things. And indeed, they can be used to do high-resolution NMR. And this is how they still look. But I wonder if in a couple of years we will also have machines, and without knowing it, or some people will know, of course, all this technology will be inside of them. And with that, thanks a lot for listening. Any question? Yeah.
I can, yeah. So two questions. So one is a follow-up of something that. Yeah. So one is a follow-up of something that you already said. That so at the moment you say let's forget about the upper level. Yeah. So what can you? Can you give me an overview of what else can you do regarding, of course, NMR with the upper level?
Yeah, okay, that's a good question. Of course, this is for me to give a talk that's more accessible, but there's many people who also think about this third level. There's people who develop control over the full space. And for example, I don't know if it has been studied for the field of NMR in particular, but one interesting thing is that, okay, let's say, if you only work with the two levels, the 0 and the 1, only the 1 is moving when you are in the presence of a magnetic field. If instead you work with the 1 and -1, which is not something I showed here, now the amount of splitting you have is double. This is, if you work in that subspace instead of the 0-1, you are more sensitive to external magnetic fields. So that's one of the ideas of using this. But of course, you can do a lot of stuff.
Thanks. And then another question. So what about the speed at which these experiments can run? So I heard that one of the big goals of this, not of NMR, but of magnetic force resonance microscopy is to image things in real time.
Yeah, indeed.
So how is this helping us?
That's a very good point. I think this took them like a week, which is, of course, a different scale to what you can do with classical NMR. But there are a lot of optimizations that people is working with. For example, in the same group, now papers that they publish afterwards is using hyperpolarization. So using hyperpolarization, of course, you can increase a lot the signal of the NMR, and then it's much, much, much faster. I think it's close to the time scale of a classical machine, maybe not so good, but around that. But of course, there is because a lot of the problems here can be things like, okay, it's very difficult to pull the fluorescence out of diamonds. We need to shape our diamond, so it's, there is a lot of room to improve, but indeed the speed is much slower, yes.
Sorry, hyperpolarization is that you transfer the nuclear to electronic spins?
Yeah, sorry. Hyperpolarization means if I do an experiment of this type, I put a sample, I put a magnetic field, the spins of my sample align with the magnetic field. This is a lie. You are going to have a Boltzmann distribution, which at room temperature is that 1 in 10,000 spins is going to align. So the signal that you have is extremely weak. There are many techniques to, through different means, align many more spins with the magnetic field, and then the signal grows by orders of magnitude.
Thanks a lot.
Do you want the cube? Okay.
Can you hear me?
Yeah.
Yes?
Yeah.
Does it work? Okay. Thank you. Thanks for your lecture. Very, very clear. You describe MV centers as very, very delicate sensors for measuring, detecting weak magnetic fields and everything. So what are the chances if you push it down to use MV centers to do quantum tomography. I mean, not just exploring the spectral properties of molecules, but just see what's the quantum state of some spin in your sample.
So you mean a different spin, not our MV?
Yeah, exactly. It's a different
yeah.
spin.
Okay, so that's a different type of beast, but of course, this is very widely studied. Here I only talked about how classical fields can interact with my MV. A very huge area of research is now, of course, we have a lot of spins that are close to my MV. Can I coherently talk with them, create entanglement, and measure them, do tomography? I know there's people who is pushing a lot this technology. For example, the group of Taminiao, I think they work with very low temperatures, and then they have very nice coherence there. They can measure the state of nearby spins. I cannot tell you to which precision, but this is a type of experiments that is done indeed. Yeah. I think or at least the record a couple of years ago was a 10-qubit spin register. So they could manipulate with a single MV 10 different qubits around.
Okay, catch it.
Congratulations for the nice talk.
Thanks.
I was wondering, everything is done with single MV, right? All this sensing?
Well, for example, in the field of NMR, there are, let's say, two branches. One is to use a single MV, and then the sensitivity is lower. Of course, you are only measuring once, but the volume you have is reduced, so you have access to maybe more interesting or more exotic measurements. In the other hand, these experiments are done with many of them. So it's a lot of MVs in a small diamond, and then the signal is higher.
I was wondering if you can perform the Ramsey sequence sequentially, so to extract information for a longer period of time, but taking advantage of the coherence of several MVs. So like in a sequence, is that something that is done?
So, for example, I know, tell me if this is similar to the thing you are thinking about. There are groups that have taken a diamond, then they make a measurement, and instead of having like a photodiode or I don't know, a sensor which is only 1 pixel, they use a camera. And then they can see an image of the signal, and then they can see really an image of the fluorescence and how the fluorescence changes differently in different parts. So, for example, you could do the ODMR experiment, but now you have a spatial resolution because you are looking at an image of the diamond. So, yeah, I imagine the same can be done with the Ramsey, for example.
Yeah, but that's with the target of measuring variations spatially,
of magnetic
right?
field, yeah.
Mm-hmm. Thank you.
Yep. Okay.
So thank you for your nice talk, very interesting. I just was wondering about, you mentioned that maybe we have NMR at cell level. How far are we from that? So from having maybe in hospitals or in medical centers, this type of machines that can help to identify tumors and things like that.
Okay. I'm not a futurologist. I don't know. I will say, okay. Of course, it also depends on if there are companies actively working on this. I have a lot of faith on this technology. So I think 10 years, let's say, I don't know.
I was just wondering because whenever you go to quantum technologies, everybody's saying that quantum sensing is the most promising regarding marketing, sales, and having available solutions. So it's just wondering if, because I have seen many talks talking about that, and I just wanted to have your view from the lab and from somebody that there is insight, right, from working on the field.
Yeah, I think this is really possible, in my opinion. Of course, then maybe in the lab, something, oh no, we didn't take into account this, who knows. But this is really possible, and in fact, it's very a humble technology compared to things like quantum computing. We are not asking a lot from this. In fact, the quantum part is just this antenna being substituted. I think if something has to work, this is going to be one of the first things. So yeah, I would expect a short time, maybe 5 years.
Okay, thank you very much.
Okay.
Maybe just out of curiosity, because I'm not familiar with these devices, how can the MV centers have such long coherence times at room temperature?
Yeah, that's a very good question. So, of course, the environment in which this MV is placed on is very special. It's a matrix of diamond, huge diamond, that then when they fabricate them in these labs, one thing they do, for example, is to isotopically purify this diamond. So diamond usually has also carbon-13, which is magnetic. They don't put carbon-13 when growing them, so it's extremely pure diamond. And yeah. But I mean, of course, there are many more reasons, like the way these defects interact with phonons and so. But yeah, it's really a very nice matrix in which to be placed.
Okay, thank you.
Okay, if anyone has any more questions, we can thank Carlos for his very interesting talk. And as you may notice, we have a couple, some more time, apart from the coffee break expected time, so just enjoy a larger break. And yeah, take a breath a little bit, and then we wait. We will just wait for the people in charge of the coffee to make it ready, and we go for it. And we see each other again at in almost an hour, in 55 minutes. Okay, to continue with the contributed talks.
We are interested in entanglement classification. This means that there may be two states that both are entangled, but they are entangled in different ways, and therefore they may be useful for different tasks. As an example, for 3-qubit states, the set of all states, we divide it into different classes. For instance, we can have separable states that contain no entanglement, biseparable ones, which have correlation between pairs of particles, and genuine multipartite entanglement, which means all 3 particles are entangled. And for instance, for the qubits, there are 2 non-equivalent classes, which are called W and J set. And as a summary, they have different properties, and they are useful for different applications. So, nevertheless, there is a problem concerning the theory of entanglement characterization. Mainly, there are 2. So, to being able to characterize the entanglement within your system, you require to have the system completely characterized. And this means that for a general unknown state, you need to perform a number of measurements that scales very bad. In particular, it scales exponentially with the number of particles in your system. And even if you are able to have your state fully characterized, still, to classify entanglement, you need to, so due to the mathematical complexity of the entanglement structure, classifying entanglement and in general characterization is a hard problem. So for the second problem, which is the mathematical complexity, to use neural networks, which don't, in order to make the method useful, you don't need to know the structure of the entanglement. The network only needs to learn from experience. However, this raises an additional concern, which is interpretability. We don't know what the model is doing, and this is a problem mostly in science. So we propose to add an extra layer, which is going to interpret the model. In particular, we are using an algorithm that for each input of the network will assign a real value, which is quantifying the importance of that particular input for the result of the network. And by doing this, we hope to obtain some inputs that are not important, and we're able to remove them, and also try to advance a little bit in the problem of having to do many measurements for entanglement characterization. So how do we propose to do it? By a 5-step process. And first, to train a network, we need a data set. To do so, we take the set of all quantum states, and we try to sample randomly and uniformly from each of the classes. We do this numerically. And once we have random states labeled with respect to entanglement that they have, we do some measurements in a complete measurement set. So in some set of measurements that completely characterizes the state. And it will be grouped in a vector that then will be used as input to the network. As for the neural network model, we are exploring 2 different types of networks, convolutional ones. These are different, but for what concerns us, convolutional neural networks are good at differentiating local patterns. This means that when processing information, they take into account local data in your input, while in dense neural networks, each time you process the next layer, you are seeing all the inputs at once, and therefore are better at general patterns, and in particular, global patterns. And this is why these are better for entanglement characterization, since entanglement is a non-local property. And finally, for interpretation, we are using a method called Shapley. So to explain it, imagine you have an input that is processed by a neural network, which is performing an unknown function f. So there you can see that if fx is the output of the network, Shapley is assigning a value to each of the to each of the inputs, which are in the y-axis, and these contribute how much they are pushing towards the result of the network. So with this, we are analyzing several types of systems. And first of all, you have pure states. Here we are presenting 2 and 3 qubits, pure states, which, as I said, are sampled randomly and uniformly. So the main property that they have is that their tomography measurements contain redundant information for entanglement classification. We see this because here you can see plots A and B, which correspond to the Shapley or the importance distributions for two different networks trained with the same data. And both output a different distribution. For instance, you can see that blue and pink bars represent the same measurements and are in very different positions. So this means that the network, when being trained, can extract the necessary information for many places, and they don't converge to a single solution. The same goes for 3 qubits. So having this redundancy has mainly two consequences for the next step, which is trying to remove as many measurements as we can to simplify the problem. So here in these plots, you can see how each time we are removing measurements, and the accuracy remains high since the network is able to take, as I said, this information for many measurements up to a point where there is not enough information and the accuracy drops. Also, you can see that it's irrelevant the order in which you are removing the measurements because, again, the network can take that information from many places. With mixed states, however, the results are different. Here for 2 qubit states, we are again sampling uniformly from the set of all quantum states. And in this case, each time you train a network with the same dataset, you obtain the exactly same distribution. It's because for mixed states, all tomography measurements are required for the complete characterization, and they all give necessary information. And also, you can see that they group in blocks, and these blocks are always the same. What I have just said can be seen by the fact that when removing measurements, each time you remove a measurement, you can see a significant drop in the accuracy. So it's not as clear as it seems to simplify the measurement reduction problem. And also, the order matters. In particular, if you go in increasing importance, so starting removing the least important ones, accuracy maintains higher for a higher amount of measurements. Here, in this 3 qubit example, we are not considering uniform states. Instead, we are considering a particular family of states, which are particularly states that are detected by some witnesses. We wanted to test if there is some structure in the set of states analyzed, if that is translated into better performance by the network. And that is, in particular, the case. So you can see that the distribution is much simpler, with many of the measurements having no importance at all for the classification. And also, the accuracy for classification is maintained high for a higher number of measurements, and you can perform a complete characterization with almost only 4 measurements out of the 64 that are required. Another great thing for which we can use this course, both for pure and mixed states, is that if you want a target accuracy, we can give you the minimum amount of measurements that you would require to perform. And on the other way around, if you have a X number of random measurements, we can give you a lower bound on the accuracy that you will obtain if you try any method of entanglement characterization. So as a conclusion, it's possible to characterize entanglement using neural networks. And we are actually benchmarking several types of architectures, and we are providing different guidelines for designing them in different scenarios. And we are testing how the Shapley method for interpretability works in this particular problem. Also, we are able to give the minimum resources required for a given accuracy for classification. And also, we are analyzing where neural networks are good at capturing physically relevant structures. For future work, first, as I told you, we are doing this numerically, so testing this on real data would be nice. Also, we are using Pauli tomography, but other more complex observables maybe work better. To escalate this to higher dimensions, maybe changing the classification method. And if we are able to escalate it, maybe to provide an scaling of the amount of resources required for classification given the dimension, and also different ways of interpreting besides importance, which may advance in how we use neural networks as a tool in quantum technologies. Thank you very much, and if you have any questions.
Thank you very much. Is there any question? Somebody? Yes.
Hi, thanks for the talk.
Thank you.
So my question is, I didn't really understand what the share Y does. So I understand that the input to the neural network are the random measurements results, right? Mm-hmm. And then the outputs would be the classes of the. Sure. But what does the share Y do in this situation?
So basically, the neural network is performing some unknown function, and so Shapley is a method that is applied to. So it's in a branch called interpretability machine learning and works in trying to understand what the model is doing. So what it does is it uses some game theory results and combinatorics to try to infer what is each of the inputs contributing to the output. So in particular, which are important, which are not important, and if they are contributing towards classification in a given class, or if they are contributing against. For instance, two different inputs may have different distributions of importances.
So it's basically for you to know which of the measurements that you did are the important ones.
Yeah, that's it. And with that information, we try to remove the ones that are not important, and therefore try to reduce the amount of resources required.
Okay, thanks.
Thank you.
Question? No? Yeah.
First, congratulations for the good talk. And as you said, you're using this with numerically, not with real data. Have you thought, your team and you, of a specific use case when you develop this method and it's more advanced and you're sure it works, of a real use case where knowing what type of entanglement would be useful for a specific experiment or something?
Yeah, so for instance, in general, so we are now trying to introduce several models of noise and different imperfections that may appear in some experiments. And the idea is, once we have the method developed, just like publish the neural network train just as a tool so that an experimentalist can use it given the number of measurements that he has available. For instance, there are some scenarios you can consider, for instance, quantum networks, where maybe the alignment between the local reference frames is difficult, or maybe you don't have control over what measurements you can do. So you can output, or you can measure a given number of random measurements, and we can give you what is the lower bound for the accuracy that you can obtain with this number of measurements. You can use the method to try to characterize the entanglement if you, in addition, know which ones you are measuring. And if you know which measurements you are doing, you can probably optimize much better for your particular case the accuracy for the classification.
Okay, thank you.
Thank you very much, Alfonso.
Thank you.
The next speaker is Francesco Flora from ICFO, Eurecat, and ICREA. And he
Okay, hi everyone. So I'm Raffaele Davino, and so I am a PhD student at ICFO, and I will talk about this project. So I want to start introducing quantum randomness and why it's important. So randomness can have many applications, like in cryptography, in numerical simulation, or foundational tests of physical theories. And randomness is a property that naturally arises in quantum mechanics because the outcomes of quantum measurement are inherently probabilistic. So for example, if we take the plus state, that is just a superposition of 0 and 1, and then we perform a measurement in the computational basis, then we will have the outcome 0 and the outcome 1 with 1/2 probability. And another property that is important is that so the outcomes are fundamentally unpredictable from the point of view of an adversary. So if we again take the same state, so this is a pure state, so cannot be correlated with any other state. Therefore, if there is an adversary that holds a system in some state sigma, then the global state will be for sure a product state. And now, after performing the measurement, on average, the state that we have is 1/2 0 tensor the state sigma plus 1/2 the state 1 tensor sigma. So again, the state is again product state. So the adversary cannot use its state sigma in any way to guess more what is the outcome. And so this is in an ideal world, but in a real implementation, we have some noise. And so we cannot prepare ideal state and measurement. So the noise that there is could arise from some correlation with a possible adversary. And this is what we want to tackle in this project. So let's see in particular the scenario that we have. So we have a prepare and measure scenario that is a very simple scenario. We can imagine that we have a lab in which there is a user that we can call Alice, in which so the Alice is preparing a state rho s, and then is measuring the state with a measurement ms, obtaining some outcome A with some statistic given by the trace of the measurement over the state. So now we consider that the measurement and the state are fully characterized, so are fully known by Alice, and this is called device-dependent framework. So they are known, but they are not trusted in the sense that the noise that there is could be in some way correlated with an adversary. So let's focus on the measurement. And so we can see, so this is the measurement MS is the measurement that we see. But actually, in the lab, there could be a different scenario. So we can imagine that there is actually a memory initialized some state rho m. And the measurement is a projective measurement that is performed globally over the state rho s and over the state rho m. Then we can also consider that outside the lab there is an adversary that has some system rho e, and that is correlated both with the state rho s and also with the state rho m in such a way that the global state is given by a pure state psi. And then what the adversary does is to perform a measurement on its system and obtain some outcome. And the goal of the adversary is to guess the outcome of Alice inside the lab. So we can see this as a game in which Alice obtains some outcome A, and the adversary is trying to obtain the same outcome outside the lab. So just to recap all the elements that we have here, we can see in orange the state and the measurement that are known by Alice. Then in blue, we have elements that are still inside the lab but are unknown. And finally, the adversarial are in red, and this is the part held by the adversary. And when we calculate the guessing probability, we optimize both on the uncharacterized part and on the adversarial part. OK, so let's see this a bit more formally. So the guessing probability can be seen as a maximization over the uncharacterized measurement, the adversarial measurement, and over the global state of the sum of all the outcomes of the probability that Alice obtained the outcome A, and at the same time, the adversary is obtaining the same outcome, with some constraint that just say that when we reduce over S, then we have, again, we recover the state rho S, the measurement MS, and the statistics, because over S, everything is fully characterized. OK, so this is something very complicated to compute, and so was not previously known. So what we did is to use a block decomposition of the measurement pi. So we write it as sum of some standard basis elements over S, tensor some operators over M. And we can do this because over S, we have a finite dimensional system given that S is completely characterized. Then we introduce some moment matrices that are some matrices indicated by the possible outcome of the adversary. So these matrices are constituted by some elements that are just the trace of just the expectation value of some operator of the identity or the operator K of the block decomposition of pi over some unknown state. I will not go into the detail of how this moment matrix is built and why we built in this way, but the main result is that we can map the problem that we saw in the previous slide of the guessing probability in another problem that is an optimization over these moment matrices. And while before the problem was untractable, here it becomes computationally efficient. So this is our main result. So now we are able to compute the guessing probability, and we can see some possible application. So a first application, so we have the depolarized state and measurement. So we have the state ρS that is just the plus state, and the measurement is the computational basis. And we have some noise given just by some linear combination with the maximally mixed state. And here there are the results that we have. So what we plot is the mean entropy that is just minus the logarithmic of the guessing probability. And this is the quantity that actually quantify how random is the output. And we have in the solid line an upper bound that was previously known, while in the dots are representing the result that we obtained with our method. And we actually match the upper bound. So we proved that that upper bound was actually the exact result. And then another application, so we have here a state. Now the state is totally uncharacterized, so ρS here is not known, while the measurement is taken as 1 over the number of outcomes multiplied by the identity plus some coefficient multiplied by the Pauli matrices. And previously was known that if the measurement is considered not trusted, so then increasing the number of outcomes, the randomness goes increasing. But now, with our method, we are able to compute it also for untrusted measurement. And we observe that for number of outcomes already equal k, the randomness drops to 0 in this scenario. OK, so now we can see just one last result. We go back to this scenario in which we have the lab and also the adversary. And in principle, we have that between ρS and ρm, there could be any correlation. But what we can also do is to impose some separability between these two systems. So that means that the global state between S and M is just a convex combination of product states. And what we observed is that we can construct a state and a measurement such that the guessing probability of the outcome from the point of view of an adversary is higher when correlation entanglement is allowed between the two systems, compared to the case in which entanglement is not allowed. OK, so this was the last one. I want just to conclude. So what we did is to study the intrinsic randomness in a characterized but untrusted prepared measure scenario. Then we derived a semi-definite formulation of the device-dependent guessing probability. And then we applied this, so before to two different scenarios. And then we showed that classical correlation between preparation and measurement can strictly reduce its predictive power. So thanks for the attention.
Thank you very much. Any question? No? I have a question for you. Does this approach work for any kind of device?
So as long as if it is finite dimensional, and you can characterize what there is in your device, so what is your state and what is your measurement, then yes, it works. So yes.
Okay, thank you very much.
Thank you.
Let's thank to Raffaele. The next speaker is Alatz Álvarez Aedo from Universidad del País Vasco. She will talk about high-dimensional digital analog quantum computing.
Right.
Yeah, I said she.
Yeah. Okay.
Basque Country, and I will talk about high-dimensional digital analog quantum computing. To do so, I'll first make a brief introduction about the two ways of doing quantum computing, which is the analog quantum computing way and the digital one. So the analog quantum computing composes of having a natural Hamiltonian in your lab, whatever it is, and using this Hamiltonian for an evolution, which usually you can tune by changing some parameters, for example, by doing quantum annealing. Now, this approach usually is more robust than the digital approach. It's less prone to noise and more resource efficient, because these Hamiltonians and these unitaries are usually tailored to the problem that you want to solve. On the other hand, because they are tailored to a specific problem, they are not as flexible, and they do not compose of a universal way of doing quantum computing. On the other hand, we have digital quantum computing, which is a very versatile way of doing quantum computing, since we have digital gates, usually C0 or a CZ, and our local unitaries. And it's also universal. You can do any quantum algorithm that you want to. But it's more prone to the environmental errors and control errors. Now, what if we were to combine the best of both worlds? We get the robustness of the analog quantum computing and the versatility and universality of the digital one. To do so, we'll need two resources, our natural Hamiltonian and single unitaries. And we will entangle this Hamiltonian, which means I will do a set of local unitary digital operators, my analog evolution, and another local digital operators, which will turn my Hamiltonian into another effective Hamiltonian. And by doing this multiple times with different possible conjugations, we'll map our Hamiltonian into a new Hamiltonian that describes our quantum algorithm. There's two ways of doing this. First, by doing the stepwise digital analog quantum computing approach, which means I apply my local unitaries, then I do my evolution for a certain time, then I do again my local unitaries. Or the banked digital analog quantum computing way, which is I leave my Hamiltonian on, and then on top of the dynamic, I apply the local unitaries. This is usually more experimental friendly, but it will introduce a small trotter error. Now, here's a brief example of how digital analog works. We have our problem Hamiltonian, which has couplings HP, and our source, which is HS. And as we see, the moment we conjugate or sandwich our Hamiltonian, we'll turn it into another effective Hamiltonian. And by doing these sequences, we'll get the mapping that we're looking for. In the case of qubits, by doing these conjugations, what we get is flipping the signs of the different couplings. We can translate these flipping signs into a system of linear equations by doing an approximation, which is I take my product of Hamiltonian, effective Hamiltonians, and I turn it into a sum, and then I have a linear system of equations where my matrix will have the information of how I'm changing my signs in the couplings with every conjugation that I'm doing. Here's an example of how it works with 3 qubits. I have a simple Ising Hamiltonian as a source with coupling J, and I want to do another Ising Hamiltonian with the same connectivity, but with couplings H. Now, if I conjugate the first and third qubit, for example, you can see that I can change the signs of the coupling 1, 2, and 2, 3. And that information is stored in the matrix. With the protocol that we have here, we can ensure, by doing all the possible combinations for an arbitrary two-body Hamiltonian, that we can get a solution that has positive time solutions, and also that there exists a solution in this system of equations. Now, the philosophy of digital analog quantum computing, in this case, is being resource effective when it comes to the NISQ era. This is going to be our top priority. So why do we want to do this now for higher dimensional systems, aka qubits? Because a lot of the problems that we can face in physics usually are not described by simply SU2 dynamics. Let's say I want to do some case theory simulations beyond set 2. My electrical field will be given, for example, by a local operator that is 3 by 3, if I do by set 3. So following the philosophy of being as resource efficient as possible, we're going to extend the paradigm to beyond SU2. To do so, we will use the Weyl-Heisenberg operator basis, which consists in the clock operator, which gives phases depending on which energy state you are at, or the shift operator, which gives how you translate between energy levels. We use this basis because it has a property that shares with the polymatrices, which is if we conjugate an element of the basis, we'll get the same element and a phase. If you look at it at the D root here, you'll see if I choose the qubit dimension, D equals 2, I get back -1, which is flipping the sign. So seems like we're in the right track. This is an example on how conjugating works. We can see that if I conjugate my shift operator, my clock operator with shift operator, I'll get the clock operator with a change of phases. Now, to showcase how this works, I'll do it for this following example. Let's say I want to develop an isotropic bilinear biquadratic Ising-like Hamiltonian for spin 1. This is very useful for condensed matter people. It's a little bit simplified. Usually has all the spin directions, but I only take the diagonal for my simulation. And my resource will be a spin Hamiltonian, which should be somewhat so standard to find in natural quantum systems. So I will first decompose my spin operators to write them in the basis that I've chosen. After doing the decomposition, we can see that, for an example for 2 qubits, these are all my possible conjugations. If I see the second one, for example, I'll see that for the different parts of my basis, which is all what that appears when I do the decomposition, how I add a phase to the different parts of my spin operator. And this will be my system of equations. It's OK if it's composed by complex numbers, because since I'm working from a real operator to another real operator, my solutions will be real for sure. That's fine. So I do a small numerical simulation to showcase how it works. In this case, for 6 qubits. And I compare it with the digital case by taking, for the digital, a superconducting circuit, and for the digital analog, an ion trap, because they kind of fit better for each other. Now, the numbers that I've used is 99.5 fidelity for my local operators. My relaxation time for my Hamiltonian is big enough. It's very usual for ion traps. And the single qubit gates are somewhat fast. And my initial state will be the GH set state. Now, we can see in the simulation that in this case, because the gate fidelity is terrible for the qubits, the main bottleneck for my digital and quantum simulation will be how many gates I apply. While for the digital one, I have a fixed number of gates for the two-body and single-body, but it oscillates because due to the nature of the noise channels that I'm using, I'll get a change of phases. You can see a somewhat similar fidelity for both of them. The changes depending on the angle that I want to do my BLBQ. But this is an important remark. I feel like the digital simulation is very tailored for this problem. And usually, if I'm going to work with QTYS, as I do with any digital quantum computing approach, I'll want to define my set of gates and then map these gates into my problem. Now, what I'm doing here for this simulation is mapping the gates into the problem. Hence why I get good results for the digital. So one could think about the result that for a universal way of solving the problem in digital quantum computing for the NISQ works as well as a tailored problem for the digital quantum computing. So in summary, we have extended the digital analog framework to QTYS. In this case, it only requires a polynomial amount of blocks, or effective Hamiltonians in this case. And we have introduced a way of building quantum algorithms by only using two types of local operators and an entangling Hamiltonian. If you know anything about QTYS simulations, you'll see that there is not a consensus of what to use. You can use if you compare it with qubits, because you are doing modulo operators, for example, for the CSUM, it's not the same going forward or backwards, because you are doing modulo 3 for the QTYS, for example. So we have a universal way of doing this. Now, regarding the outlook or the future projects, we are working on using now our D-level local structures to naturally do gates theory simulations, because now we have the resources of how to map these natural resources into our physical problem. We are also looking into extending the construction beyond two-body Hamiltonians. That means doing many-body Hamiltonian simulation using digital analog quantum computing. And we also want to extend digital analog simulation to Hamiltonian functions. This means doing nonlinear simulations. As you've noticed, I'm mapping this into a linear system of equations, but imagine I want to do the sinus of a Hamiltonian. For the moment, I cannot do this, but this is a future project to give a certain completeness. Like, let's say I want to build a quantum computer that uses digital analog. I need this completeness. So we are working on this. So thank you very much for listening. And if there's any questions.
Questions? Espera, toma otro.
Okay. So my question is, do you have any candidate system that could be adequate to implement this extension of digital analog?
So mainly, in my opinion, either ion traps or Rydberg atoms. But for me, my favorite one is ion traps. Okay. They have a Molmer-Sørensen that you can apply to an all-to-all connectivity. Well, you can change the connectivity depending on the laser, but mainly all-to-all, and it works very good.
And have you explored how to implement specifically the two operators that you propose, the X and Z?
So these two operators, they already have it designed in, they have a paper in Innsbruck, which is called QT Quantum Processor. They already do the mapping of the local Molmer-Sørensen into these kind of operators. The numbers that I give here for the simulation, this fidelity comes from their paper.
Okay. Thanks a lot.
More questions? Thank you very much, Alats. Okay, and last but not least, Tomás Fernández Martos from ICFO. He will talk about deterministic randomized extraction for quantum random number generation with partial trust.
Hello. Can you hear me? Yes. Okay. So I'm Tomás Fernández. I'm doing an industrial PhD between ICFO and QSite. And as you can see, the title is quite long. So to unpack it, I thought that it would be important to do a thorough introduction of everything I'm going to be talking about. So without further ado, so this talk has a big overlap with what my colleague Rafael already talked about 2 talks ago. Essentially, well, as you know, random numbers are a very important resource for cryptography, among other applications. But in particular for cryptography, there are 2 properties that they need to fulfill, which are uniformity and unpredictability. And this is very simple to visualize. You can just think of a set of dice, and unpredictability is that you expect to not be able to predict which side is going to end up facing up when you throw it. And uniformity is just related to the fact that when you throw it many times, you expect that the outcomes appear, on average, about the same proportion of times. Now, an important caveat that one needs to take into account is that physical devices have noise and may have correlations with the environment, and this can affect, in particular, the unpredictability. To illustrate this, think again about the dice. You may throw them many times and record the outputs in 2 different sheets of paper. Now, if you take one of those sheets of paper as your system, you can think about the numbers that are recorded in the sheet of paper as being a source of uniform random numbers. However, in this case, they are completely predictable because you have the exact same random numbers on the other sheet of paper that is part of the environment. This is a very extreme example. In practice, you don't have a 100% correlation with the environment, but you do have some. And in the cryptography world, this is what we call signed information. And it's very important to quantify it in order to assess the security of a QRNG or RNG device. Now, in terms of the quantum formalism, thinking now about sequences of random bits, the quantum state that describes a sequence of uniform and unpredictable random bits is this one here, which is just a maximally mixed state that's uncorrelated with the environment. And a more realistic one is this one here, where we have some randomness distribution that is not necessarily uniform and some amount of correlation with the environment. This is what's usually called a classical quantum state. And a non-trivial thing is how to go from the side information notion to the classical quantum state that describes how the side information affects the system. So this is one of the central tasks in assessing the security of random number generators. So then, a quantum random number generator is simply a device that makes use of the inherent randomness present in quantum systems in order to generate random numbers that are near perfectly uniform and unpredictable. In particular, they will generate an initial sequence of bits that can be described by a classical quantum state. And then after some post-processing called extraction, we will get a shorter sequence of bits that will be epsilon close to being the perfect sequence described by this quantum state that I mentioned before. And diagrammatically, a QRNG looks like this. We have one element that's the quantum entropy source containing the quantum system and the measurement device that measures its behavior. That outputs the raw sequence of bits that is then refined by the extractor into the final near perfect sequence of bits. And in order to quantify the efficiency of an extractor, this can be lower bounded by the conditional mean entropy, as Rafael also mentioned before, which is simply minus the logarithm of the guessing probability. I said simply, but this is not simple at all. Estimating the guessing probability, which is the probability for an adversary to guess the outcome of a quantum entropy source where that outcome is described by a certain classical quantum state. This is not trivial, and it's also a central task in assessing the security of QRNGs. OK, that's one of the terms of the title. Now we go specifically onto randomness extractors. And randomness extractors, as I said, are the post-processing step that refine the raw sequence of bits into the near-perfect one. And it turns out that most of them actually require the use of a seed, which is an additional input, a short string of bits, that needs to be also near-perfect and needs to be independent from the raw sequence of bits that we want to refine. And mathematically, it's simply a function that looks like this. And it takes our classical quantum state, to a state that, again, is epsilon close to being perfect, but I just added here the system for the seed. And one very important condition that this extractor requires is that the conditional mean entropy associated to the classical quantum state that describes the sequence that we want to refine needs to be bounded by some quantity. And estimating this bound lets us know how long is the final string of bits that we're going to be able to obtain with the extractor. Okay, so now deterministic randomized extraction is the same kind of routine, but without a seed. It's simply just a deterministic function that takes a string of n bits and refines it into a shorter string of n bits that are epsilon perfect. But then what are the requirements for deterministic extraction, and how can we actually perform it? Well, it turns out that we didn't know until last year, but I will talk a bit more about that later, because now we're going to the last term of the title, which was this partial trust that was mentioned. And for that, I need to talk about the assumptions that one can make when we devise a QRNG protocol. And we can place the assumptions on two different parts, either on the device or on a hypothetical attacker that's in control of the environment that may affect our device. And we can constrain that attacker to hold either classical information or quantum information. And if we consider that it can hold quantum information, then we say that our protocol is quantum proof. Okay, so this is the classical quantum state that we had before. And then the idea here is that the set of classical quantum states compatible with the output of a quantum entropy source depends on what the assumptions that we pose onto the quantum entropy source elements themselves. The simplest kind of scenario is the device-dependent one, which Rafael again before mentioned, where we give an explicit description of all the parts of our device. So we give an explicit description of the quantum state that we prepare and the measurement that we implement. This gives the better results in terms of entropy, but and it's the easiest to implement in practice, but requires a lot of logical elements to verify that the assumptions hold. And the part of the trust is related to the possible noise, either in the preparation or in the measurement. So if we allow the adversary to be correlated with this noise, we would say that that specific part of the device would be untrusted. On the other side of the spectrum, there's the device-independent scenario, in which we place zero trust on the whole device. We treat it as a black box, and the security and the set of classical quantum states are assessed based only on the statistics that we can observe in an experiment. This is the most robust in terms of security, because the adversary is the most powerful, but it's the hardest to implement in practice. Then there's a middle ground, which is actually the more interesting one, in which we only give a partial characterization of our device, and we also have generally only partial trust on some of the elements. We can have either a black box for the preparation, the measurement, or the whole system with some caveats. For instance, we can consider that we're bounding the dimensionality of the system or the energy that the states that we prepare can have. Okay, now that I finished with the introduction, I will be very brief with the results, I promise. So this paper that I mentioned last year by Cameron Forman and Luis Massanes, here basically they showed the first quantum-proof deterministic randomized extraction protocol, because for classical adversaries, some already existed. And they do it in a device-independent scenario, so the device is a black box. And they do it for an entanglement-based setup, mainly because they use the fact that there's a violation of a Bell inequality. But this is not too relevant in our case, because what we do is extend this to a prepare and measure scenario, which is what I've been describing, for different levels of partial trust and different levels of characterization. The schematics look like this, and I'll go over them one by one. So the first one is an untrusted preparation scenario, in which we do not trust the state preparation. And we have a binary outcome measurement that we trust and is characterized, so we give an explicit description. Then we have the symmetric case, in which the measurement is untrusted, and we have a trusted and characterized preparation. And finally, we have a third case, which is somewhat similar to the second one, but now it's a semi-device independent one, where we have two trusted preparations, for which we only describe a lower bound on their fidelity. And we have a binary outcome measurement that is untrusted. Okay, so essentially, the gist of it relies on showing that there exists some operators such that we can have randomized extraction, deterministic randomized extraction, which entails to showing that we have that the security condition here holds. And without going into too much detail, because it would be a bit too much, I'm just going to mention that we proved this for the XOR single-bit extractor, which is just an extractor that applies the XOR function to the input. And then a particular family of multi-bit extractors that have a sort of randomized construction. OK, now the last result slide is some numerical results in which we simulate a QRNG protocol, in particular in the third scenario, the semi-device independent one. And here we model experimentally relevant behavior, which is the input-output probability distribution that we will have with a, let's say, perfect device, in terms of some parameter delta. And these are the numerical results that we obtain, where the relevant part here is that we basically estimate the amount of bits that we can get, or the rate of extractions that we can get for protocols of varying number of rounds. And the important result is that we can get positive randomized extraction for, in the best case, for a protocol of only 7,000 rounds, which is a somewhat remarkable result. And then we also include everyone's favorite noise, which is white noise. That is, everyone knows is the best way to model noise. And then we show the resilience that this protocol has while including this white noise, and compare it to some more or less equivalent protocol. And in our case, our protocol shows about 2 orders of magnitude more resilience to noise than the one that they report in that other paper. And so that's basically it. As concluding remarks, just simply want to mention that we finally, after a lot of time, have deterministic randomness extraction. It was pioneered by Cameron Massanes for device-independent scenarios, but now we extended it to prepare and measure scenarios with different levels of asymmetric trust and characterization. And we further expect this to be generalizable to other scenarios. For instance, the general device-dependent scenario where everything is untrusted, which was the one that Raffaele mentioned. And with respect to our numerical results, we basically had that a very small number of rounds required to have positive extraction and promising resilience towards noise. However, the results that we get are still significantly worse than what you can get with any kind of seeded extractor. However, that is to be expected because we are taking out assumptions and we're making the protocol more secure. So you're always going to get worse results. However, hopefully in the future we can get deterministic extraction with some better rates. And that will be all. Thank you very much.
Thank you, Thomas. Questions for Thomas? No? Okay, I have one. Okay. Is this something that can be tested on real hardware already or soon?
So due to the nature of... OK, so for the XOR extraction, in principle, it can. So that's a kind of extractor that we could try to show. However, it's not as interesting because it's a single-bit extractor, meaning that you take an input of length n and you output a single bit. So it's not practical at all. It's just more of a proof of concept. Then for the family of multiple-bit extractors, as I briefly mentioned, they have a randomized construction. Well, actually, they have it is a randomized non-constructive proof. So we don't have an explicit form of these extractor functions, so we cannot yet implement them. Hopefully, at some point, we're able to find some multi-bit extractors for which we have an explicit construction, and then we would be able to show this, because precisely this experimentally motivated behavior is based on some device that we're developing over at QSite. But for now, it's still just a theoretical work.
OK, thank you very much.
Thank you.
So that was all for the contributing session. I think we have a break now of half an hour or so. So thank you very much for the attendance and the questions.